Welcome to RenEnergy.com, your renewable energy and sustainability platform. In the modern world, with climate change becoming a significant concern, the search for renewable and clean energy sources is more critical than ever before. One promising candidate is hydrogen fuel cells, which generate electricity through an electrochemical process and emit only water as a byproduct. Hydrogen fuel cells are highly efficient, scalable, and versatile, and they can be used in a variety of applications, from powering vehicles to providing grid-scale energy storage. However, optimizing the performance of hydrogen fuel cells is a complex task, as it involves managing many interacting variables and dealing with nonlinear dynamics. It is here that machine learning, a branch of artificial intelligence that involves the creation and application of algorithms that can learn from and make decisions or predictions based on data, comes into play. Machine learning algorithms can process vast amounts of data, identify patterns and correlations, and make predictions, making them ideally suited to tackling the challenge of fuel cell optimization. The convergence of hydrogen fuel cells and machine learning. The intersection of hydrogen fuel cells and machine learning is a field ripe with potential. The complex interactions and variables in a fuel cell, which can be difficult for traditional optimization methods to handle, are well suited to machine learning strengths. Machine learning algorithms can analyze large datasets from fuel cell operations, including temperature, pressure, humidity, flow rates, and other parameters, and identify patterns and relationships that may not be apparent using traditional methods. By learning from historical data and continuously updating its understanding as new data becomes available, machine learning can enable more accurate and robust predictions of fuel cell performance under different operating conditions. Furthermore, machine learning algorithms can optimize multiple variables simultaneously, potentially leading to more efficient and reliable operation of hydrogen fuel cells. In this series of articles, we delve into the role of machine learning in hydrogen fuel cell optimization, discussing key operational parameters, case studies, and potential future directions. We hope that this provides a useful overview of the current state of the art and the promising opportunities in this exciting area. Key operational parameters of hydrogen fuel cells. The performance and efficiency of a hydrogen fuel cell are influenced by several key operational parameters. Understanding and controlling these parameters is crucial to the optimal operation of the fuel cell. In this section, we delve into some of these critical operational parameters and how they can be optimized using machine learning. Operating temperature. The temperature at which a fuel cell operates can significantly impact its efficiency and durability. High temperatures can increase the rate of electrochemical reactions, potentially improving efficiency, but can also accelerate component degradation. Conversely, low temperatures can slow down the reactions, leading to reduced power output. Machine learning algorithms can analyze data on various performance metrics under different operating temperatures to predict the optimal temperature for given operating conditions. Pressure levels. The pressure levels within a fuel cell, particularly at the anode and cathode, influence the rate of the electrochemical reactions, and hence the power output. Managing these pressures is crucial for maximizing efficiency and preventing damage to the fuel cell components. Machine learning can be used to predict optimal pressure levels based on historical data and real-time operating conditions. Flow rates of hydrogen and oxygen. The flow rates of hydrogen fuel and the oxygen, or air, supplied to the fuel cell also significantly affect its performance. Optimal flow rates ensure maximum power generation while minimizing fuel wastage. Machine learning can help determine these optimal flow rates by analyzing data from various operating conditions and performance levels. Humidity levels. The humidity levels within a fuel cell, especially in the proton exchange membrane, affect its conductivity and performance. Maintaining optimal humidity levels is crucial to ensure efficient proton transport and prevent membrane dehydration or flooding. Machine learning can be used to predict and maintain these optimal levels based on various operating conditions and performance metrics. Stack voltage and current. The stack voltage, total voltage across all the cells in the stack, and the current are direct measures of the fuel cell's power output. Machine learning can be used to optimize operating conditions that affect these parameters, thereby maximizing power output for a given amount of fuel. Efficiency. Overall efficiency is a critical performance metric for any energy system, and hydrogen fuel cells are no exception. Machine learning can be used to predict and maximize efficiency by optimizing a combination of the above parameters to get the highest possible power output for a given amount of fuel. Health and durability. The lifetime and durability of a fuel cell can be significantly influenced by how well potential failures and degradation are managed. Machine learning models can predict the onset of such issues, allowing for early intervention and thereby improving the cell's lifespan and durability. These key operational parameters provide a starting point for understanding how machine learning can optimize a hydrogen fuel cell's performance. However, it's important to note that each type of fuel cell, for example, PEM, SOFC, etc., and its particular application may require a unique combination of these parameters to be optimized. Case studies and practical applications of machine learning in hydrogen fuel cells. To appreciate the practical benefits of applying machine learning to hydrogen fuel cells, we will look at various case studies and applications that illustrate the implementation of this technology. From support vector machines, SVMs, to reinforcement learning and infrastructure planning, these instances show the power of machine learning to optimize and improve fuel cell performance and operation. Support vector machines, SVMs, in fuel cell systems. Support vector machines, SVMs, are a set of supervised learning methods used for classification, regression, and outliers detection. In the context of hydrogen fuel cells, SVMs can be used to model and predict the fuel cell's behavior based on operational data. In one study, an SVM model was developed to predict the voltage of a proton exchange membrane fuel cell, PEMC, under various operating conditions. The model was trained on a dataset consisting of temperature, pressure, and humidity levels, along with the corresponding cell voltage. The SVM model was able to predict the cell voltage with high accuracy, demonstrating its potential for real-time control of fuel cell systems. Reinforcement learning for real-time control of fuel cell systems. Reinforcement learning is a type of machine learning where an agent learns to make decisions by taking actions in an environment to maximize some notion of cumulative reward. For hydrogen fuel cells, reinforcement learning can be used to develop intelligent control systems that optimize operational parameters in real time. One notable example is a project that developed a reinforcement learning-based controller for a PEM fuel cell system. The controller was designed to adjust the hydrogen and air flow rates to maximize the system's efficiency. The project demonstrated that reinforcement learning could effectively control the fuel cell system in real time, leading to significant improvements in efficiency and power output. Machine learning in hydrogen infrastructure planning and operation. Machine learning can also play a significant role in the broader hydrogen economy, particularly in the planning and operation of hydrogen infrastructure. For instance, machine learning algorithms can be used to predict the demand for hydrogen in different regions and optimize the location and capacity of hydrogen production and refueling facilities. In one case, a machine learning model was developed to predict future hydrogen demand based on historical usage data and socioeconomic factors. The model's predictions were used to plan the expansion of a hydrogen refueling network, resulting in a more efficient and cost-effective infrastructure. These case studies demonstrate the immense potential of machine learning in optimizing hydrogen fuel cell systems and the broader hydrogen economy. By leveraging these advanced algorithms, we can significantly improve the performance, efficiency, and sustainability of hydrogen as a clean energy source. Challenges in adopting machine learning for hydrogen fuel cell optimization. While machine learning presents substantial opportunities for optimizing hydrogen fuel cells, it is not without its challenges. These obstacles range from the quality and availability of data, the interpretability of machine learning models, to model validation and uncertainty quantification. Data quality and availability. Machine learning algorithms require large amounts of high-quality data to be effective. However, obtaining this data for hydrogen fuel cells can be challenging due to limitations in measurement technology, privacy concerns, or the novelty of the application area. Interpretability and transparency. The black box nature of many machine learning models, particularly deep learning models, can make it difficult to interpret why a model made a particular prediction or decision. This can be problematic in high-stakes applications where errors can have significant consequences, and there is a need to understand the model's reasoning for trust and regulatory compliance. Model validation and uncertainty quantification. Validating that a machine learning model accurately represents the true underlying relationships in the data and not merely overfitting to the training data is a critical task. Similarly, quantifying the uncertainty or confidence in a model's predictions can also be challenging, especially when dealing with complex and dynamic systems like fuel cells. Conclusion. Machine learning brings a new level of sophistication to the optimization of hydrogen fuel cells. Its ability to handle complex, nonlinear relationships and make predictions based on large datasets makes it a powerful tool for optimizing operational parameters and predicting system behavior. However, the application of machine learning in this domain is not without challenges. Ensuring the availability of high-quality data, improving the interpretability of machine learning models, and effectively validating models and quantifying uncertainty are all areas that require further work. Future perspectives. Despite these challenges, the future of machine learning and hydrogen fuel cell technology looks promising. As the field of machine learning continues to evolve, we can expect more advanced techniques to be developed that could further enhance the design and operation of hydrogen fuel cells and related infrastructure. Moreover, with ongoing research and collaboration between experts in machine learning, energy systems, and other relevant fields, we can overcome the existing challenges and unlock the full potential of machine learning in optimizing hydrogen fuel cell performance. Also, as machine learning becomes more integrated into our energy systems, it will be crucial to consider broader societal and ethical issues, such as data privacy, algorithmic fairness, and the impact on jobs and skills. These considerations will be key to ensuring that the benefits of machine learning are realized in a responsible and inclusive manner. Harnessing machine learning to optimize hydrogen fuel cell performance is an exciting and promising area of research that holds the potential to significantly enhance the efficiency, reliability, and sustainability of our future energy systems. Thank you for choosing ReneEnergy.com as your go-to source for all things renewable energy and sustainability. With our YouTube channel, we explore the latest developments and innovations in the field, including hydrogen fuel cells and the use of AI and machine learning to optimize energy consumption. If you're ready to take the next step towards a cleaner, more sustainable future, visit us at ReneEnergy.com and discover the many ways we can help you transition to renewable energy. Thank you for watching and subscribing. Stay up to date on all the latest news and insights by subscribing today.